Hello everyone. In this chapters, we are going to study the three-body problems. First topic is the Trojan asteroid. Second topic is the three-body problems. Third topic is equations of motions. It's better to consider the three-body problem in the rotating frames. So fourth topic is the rotating systems. And the fifth topic, we introduce the conserved quantities, the Jacobi integrals. The sixth topics, we find the equilibrium point. And in the last topic, we consider the stability of equilibrium points. First topic is the Trojan asteroid. The Sun is located at the centers, and the Jupiter is rotating around the Sun. Then Trojan asteroid exists into the two regions, L sub 4 and L sub 5. If you draw the triangles, center of the Trojan asteroid, can create the equilateral triangles. This is 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees. Maybe we could explain why the number of asteroids are located in these two positions. Then we'd like to move to the next topic. The three-body problems. We consider three objects with masses m sub 1, m sub 2, and these three objects interact gravitationally. So this is a gravitational force acting between the two objects. Unfortunately, we could not solve the equations gravitationally interacting three-body problems. We could not discover any analytical solutions of these questions. It's too complicated. So we have to simplify the problems that are restricted three-body problems. So in these problems, we consider the mass of m is much smaller than the mass of the m sub 1 and m sub 2. Because of such a small mass, motion of the m sub 1 and m sub 2 not affected by the gravitational force of the object with mass of m. But an object with a mass of the m is attracted gravitationally by the two objects, masses of the m sub 1, m sub 2. The meaning of the restricted. Then we'd like to simplify it more. So still question is a little bit complicated. The next simplification is a circular restricted. So restricted meaning I explain. And the circular is another simplification. In this case, we considered orbit of the object with masses m sub 1 and m sub 2 make a circular orbit around their center of mass. This is second simplification. We would like to examine the motion of a particle with mass m under the gravitational forces of object with masses m sub 1 and m sub 2. So to describe the circular orbit, what this means, so we consider two objects, m sub 1 and m sub 2, and making a circular motions around the center of mass. This is the center of mass. So when the object with m sub 2 is moving to this position, then m sub 1 is also moving to the new position. Then center of mass doesn't move. This is m sub 2, m sub 1. And the distance between the two objects doesn't change. This is the meaning of the circular orbit. So equation for these two objects can be expressed mu r sub 1 to second derivative with respect to time. This is acceleration. Equal minus g m sub 1 m sub 2 over r sub 1 to cube r vectors sub 1 2. This is the equation of motion, relative motion for the two objects we have studied. And the mu is a reduced mass. Mu is m sub 1 m sub 2 over m sub 1 plus m sub 2. This is a reduced mass. For a circular orbit, acceleration can be expressed mu r sub 1 2 omega squares. Omega is the angular velocities equal g m sub 1 m sub 2 over r sub 1 2 squares for the circular orbit. Then actually you can substitute this mu is here. Then we discovered omega. Omega squares equals g m sub 1 plus m sub 2 over r sub 1 2 cube. So this is angular velocity. This is constant angular velocities. So this is exactly equal to this. Angular velocity is a constant quantity because m sub 1 and m sub 2 is constant. And in this case, from the assumption, circular restricted three-body problem. Circular meaning r sub 1 2 is constant. So these m sub 1, m sub 2, r sub 1 2 is constant. So omega is a constant quantity. Then we'd like to write down the equations, motions. So we have already solved the equation for the object m sub 1 and m sub 2. So question is that we'd like to find out the motion of the object with mass of m. This m. So equation of motions is expressed mass times acceleration equal gravitational force. So this is a gravitational force acting on the object with mass of m from the m sub 1. R sub 1 minus r. You consider this is the position of origin. This is r sub 1 vectors. This is r vectors. Then this is negative r vectors. So this vectors is expressed r sub 1 minus r vector. So this is actually equal to this one. And then a little bit strange one is r sub 1 minus r vectors. This magnitude we expressed r sub 1. We often write down the magnitude of the r sub 1 vector is r1, but in this case it's not true. So we are a little bit confused quantities. So you got to be careful about this one. Also, magnitude of r sub 2 minus r vector is r sub 2. The second terms correspond to gravitational force acting on the object with mass of the m from the object mass of the m sub 2. Then we'd like to write under this equation motion in the inertial frames. So guzai eta theta is the inertial frames. So in these systems, center of mass of the object m sub 1 and m sub 2, this position is located at the origin. Then guzai eta plane is a plane on which orbits of the object with masses m sub 1 and m sub 2 are located. So this means theta sub 1 equals 0 and theta sub 2 equals 0. So m sub 1 and m sub 2 located on the guzai eta planes. But the object with mass m is not located on the planes. So this object can move freely out of the planes. So coordinate is a guzai, eta, and theta. So equation is expressed in the 3D. So equation for the guzai and then eta, and this is the acceleration. Eta and theta. The distance here and here. Actually, distance between the two objects is r sub 1 2. Distance between the two, r sub 1 2. Then, actually, maybe it's better to find out the position of the center of mass. We consider two objects, m sub 1 and m sub 2, and connecting the two objects. Then distance between the two objects is r sub 1 2. Then center of mass is here. This is center of mass. So this distance is expressed m sub 2 over m sub 1 plus m sub 2 r sub 1 2. So this distance is expressed m sub 1 over m sub 1 plus m sub 2 r sub 1 2. Okay. The equation motions in the inertial system with a coordinate of the guzai, eta, and theta. Okay, this is the end of this session.